Okay, so quick summary on the intro to the Bohr model and quantum mechanical model. These are two models that are actually built off of the wave particle duality principle. The idea that matter and energy actually have similar characteristics from which we can quantize from either end. So the Bohr model was the first model, and it was mainly significant for the fact that it revealed to us that the atom wasn't just this dense center, because that was discovered pretty early on by Rutherford, gold foil experiment. But it wasn't just this dense center and just a cloud of electrons just floating through. There was a system, an order. And not only was it an order like, oh, I can categorize, but it was a quantized order. It was an order that contained discrete amounts of energy related to the distance between those orbits, or those energy levels, or those rows on a periodic table. And so the Bohr model revealed something about how we arrange those atoms and how we quantize it with energy. Then we skip like hundreds of years later to the quantum mechanical model. And the quantum mechanical model offers us a 3D understanding of the atom, because in the end, Bohr's is a 2D picture. It's a target. It's like bing, 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 bing. Okay. And by the way, all those bings, okay, they get smaller distance between them. As you go out on a Bohr model and in actual reality, the difference between the energy levels are smaller and smaller and smaller as you go. So the greatest energy difference is between level 1 and level 2, orbit 1 and orbit 2, row 1, row 2, or principal quantum number 1, 2. All right. And so what we see is the quantum mechanical model offers us a 3D understanding based on the wave-like behavior. And it really, like Liam said, is telling us about an area of probability, not an actual ring, but that area of probability has an exact number. So a probability space is an exact energy amount. And so that's what we're getting at. And it offers us a much more exact definition of where an electron is in an atom, because we care about where electrons are in an atom. The arrangement, the internal structure of you matters. You don't want your femur on your head. You want your femur in your body, but that's not good enough. You want your femur where it needs to be to create the functional aspects that you want it to have. So that's why we care about knowing where these electrons are at their exact location. And the quantum mechanical model offers us that. Now, in college, you'll learn about molecular orbital theory, and that's a whole different level of quantized mathematical illustration of really how to look at the electron like dynamic, but we're not there yet. And honestly, it's even above me because I studied that for 2 years and I still don't know what it is. So, but quantum mechanical model is like the step in between that you guys are going to be asked to learn. Yes.
For clarification, are electrons always moving?
Yes, they are always spinning. And so we have this four element system. The quantum mechanical model has 4 numbers to it. The principal quantum number is your energy level. That is similar to Bohr, just 3D. Then you have the orbitals, TALs, orbitals. Think 3D. You just added 3 more letters from orbit, ALS, 3D. Okay. You have these now regions, S, P, D, and F. And those regions are actually co-constructed through suborbitals that are based off of the orientation in space. Each suborbital carries 2 electrons. As a whole, as a composite score of suborbitals, S carries 2 max. Composite of the 3 suborbitals for P carries 6 max electrons. Composite of the 5 suborbitals for D, okay, carries 10 electrons max. Notice, oh, hold on. So these orbitals have discrete energies as well within the energy levels. Okay, we're increasing our specificity of where the electrons are located. These sub-orientations are all about the 3D arrangement in space, and they too have a unique shape. In fact, well, never mind. I won't say that on recording. So anyway, then we have, okay, the suborbitals are also known as the angular, let's see, what is that? The magnetic quantum number. That's your suborbitals, okay? And they together composite the orbitals, or the angular momentum quantum number. And then you have spin. Spin is what makes it unique. Spin is what is the final part of your address, kind of like a house number in a neighborhood, that makes your electron the only electron in that atom at that location. And the spin is all about its magnetic pole, north or south. Okay. The term degenerate orbital sounds terrible. It just means an orientation, a suborbital with the same overall energy, because it's used to composite a complete orbital, right? So that's the big idea, is that the suborbitals don't have different energies than the orbital itself that it's making up. All right. So that's the overall idea. We're going to go through the periodic table, and you're going to see how the periodic table tells you exactly what the structure of the atom is based on the quantum mechanical model. And you guys, if you already picked up a periodic table, you already have a sneak peek. If you flipped over your periodic table that you grabbed from me yesterday, you'll see how we section off the orbitals on the periodic table structure. So go ahead and quickly flip it over. Good, Hosby, hold it up. What you see is on that. You see an outline of the periodic table, and you actually see the orbitals and the energy, principal quantum energy levels listed according to the structure of the periodic table itself. And I totally see you right now. So that's kind of the overview. Your periodic table, we're going to walk through it. It is the greatest model out there. Like, forget Vogue, forget GQ, guys. This model is the sexiest thing alive out there. Okay. It's huge. It's just awesome. It's so complicated. It's got style. It's got finesse. Okay. It's got layers that you ain't ever seen before. Gucci ain't got nothing on it. Okay. So, are we ready to dig into it a wee bit more? Yeah? Yeah? Okay. So, let me get my notes. So you watch the overview. Let's look at electron configuration, a notation that we use, all right, to start unpacking the quantum mechanical model. This is like writing out the address for for one electron, and also various electrons that make up an atom in general. All right, so it's a notation based on the quantum mechanical model that shows, okay, I'm going to say the electron arrangement in an atom based on the principal and angular momentum quantum numbers. Please tell me I'm recording. Yes, angular momentum quantum numbers. I've done a class where I didn't record the whole thing after like the first 5 minutes, and I almost like shed a tear. Quantum numbers. At some point, I will probably cry in this class, but don't worry, it'll probably be happy tears, unless it's after a bad test. I will cry with you. Okay. Hopefully that bought you some time. Okay, so key principle, Aufbau principle. Aufbau is literally German for build up, build from the ground up. Okay, so today you are Bob the Builders. You are a German Bob the Builder with electrons. And what we say is, well, how do we know? We know this conceptual ground state that we want to be as close to the nucleus as possible. Kind of like what you want to be close to your little boo thing, right? You want to be as close to the nucleus as possible, your little energy source, okay? And so we know that conceptually that we have this specific pre-designated arrangement preference, but why? And, scientists, we're just not creative, guys. We just have to name it like it is. So what did we do? We slapped a principle on it, and we were like, this is called the Aufbau principle, okay? Named after not that guy that discovered it. So what it tells us is that we literally translate it from build from the bottom up. And by the way, some of the original chemists were Germans for very clearly historical reasons. Okay, so no, seriously, that's one of the reasons why they made some of the greatest discoveries, not specifically that one, but like they were very advanced. Okay, so what we say is that we always occupy the lowest energy level first. In like 20 years, this might get canceled. Who knows? Occupy the lowest energy level first. And this is called the ground state electron configuration. So I've already said ground state arrangement. Now we're going to add on a more specific term, ground state electron configuration. Okay. And so this brings us into how do we write electron configurations? How do we write the address of an electron using the first two numbers in the quantum mechanical model? All right. And so what we have here is an example electron configuration. Now I'm going to write it as EC. Now, some of you guys are going to get excited one day because you're going to see on the agenda, it says E.C. You're going to think, oh my God, it's extra credit. Psych. It's electron configuration, folks. But it's like extra credit because it's such a freebie topic. It's just, you're going to wish you came back to this term 2, term 4. You're going to be like, oh my God, that was so easy. That was a good life. Okay. So what we say is that at the subscripts, okay, represent the number of electrons in that specific orbital. Ooh, my handwriting is already degrading. Look at that. In that specific orbital, in that. Interesting. Okay. So let's do beryllium together. So if I pull up, sorry, sorry, I apologize. I'm really just a kid inside. I just don't get to. Well, I look like a child too, but so if we pull up the periodic table, this is what you're gonna actually decorate. This is what you're gonna color in, okay? What we wanna do is we wanna write the electron configuration according for beryllium. So what we say is the first two columns are the s orbital. They represent the electrons that would stay in the s orbital. We have a 1s, we have a 2s, we have a 3s, we have a 4s, we have a 5, a 6, and a 7s, okay? But then we have the last 6 columns are the p orbital. They represent the p zones, okay? The middle section is called the d orbital. Now, the d orbital is always one energy level lower than what you think it is when you read across, okay? It's tripping, but here's why. There's a real reason. It's called nuclear effect, nuclear shielding effect, and I'm going to talk about it tomorrow, okay? This is why we see that the d orbitals are actually at a lower energy level than you would think they are, okay? Because, yeah, anyway. There's going to be some weird terminology in the future, guys, just so you know. I'm going to say some weird things that out of context sounds real bad, okay? It is chemistry. That's it. Okay, then there's intertransition metals. That's called the F block. I say the do not F with it block because this stuff is the nuclear zone. This is the cray-cray area, okay? And it's also crazy in terms of the 3D orbital structure. It's insane, okay? And this is what we call intertransition metals. That's the F block. It's 2 energy levels lower than what you think it is. 2 energy levels lower than what you think it is. So let's look at the electron configuration of beryllium. So what we have here is we would say, by the way, if you're already noticing that hydrogen is weird, why is hydrogen over here? Valence electrons, that's what's going to matter. And you're going to learn about those also tomorrow. Okay. But it's all about its chemical behavior. So hydrogen is in row 1. Okay. Row 1. S orbital. And to get to beryllium, it's 4 electrons. 2 of those are filled into the 1s2. They're in, and 2 of those electrons out of the 4 that neutral beryllium has, okay, which of course is going to be the same number of electrons as the proton count to be neutral. 2 out of the 4 electrons of beryllium are going to be in row 1, okay, orbital s2. It fills it. It maxes it out right there, okay? That's part of its electron configuration for beryllium. Remember, we're building from the ground up. Row 1 is closest to the nucleus. So we're going to fill in row 1 first, right? It's like filing into an auditorium. Yeah. Then to get to beryllium, you go over, again, now you don't snake it. This is no switchback time. We go all the way back to the beginning. And we say, okay, now I have 2 more electrons to put for beryllium. Where do they go? Where are its locations? Okay. It is 2, row 2. Principal quantum number 2, orbital s, and there's 2 of them. And that is the electron configuration of beryllium, right there. So let's go ahead and go back to our notes. And this becomes 1s2, 2s2. Boom. That's the electron configuration. It's all about reading the periodic table, the greatest model in the world. Okay. So how about sulfur? Why don't you try sulfur on your own and then I'll walk you through titanium. All right, so sulfur. Okay, what did we get for sulfur? Could somebody tell me the electron configuration for sulfur? Damn. You made eye contact. It was a mistake. Go.
Well, 1p6 is what it starts with, right?
Aufbau principle from the ground up? You just skipped. But where is 1p?
Because it's in the p block, right? So what did it start with?
But you have to account for all of its electrons.
Oh, okay. So it'll be 1s2
Mm,
and then 1p6.
there's no 1p. There's
That's
no.
in the p block.
Oh, but that. Oh, helium is technically an S block. It's just written in the P zone.
Yeah, but we're talking about sulfur.
Yeah, but I'm saying that the electrons up to that fill helium spot to get to sulfur is technically an S. Oh, that's right. I forgot to mention that one. Okay, so here's something fun about the electron configuration of helium and hydrogen and what they represent is they don't make sense at all. So, hydrogen is a non-metal, but in the metal zone, but it's row 1, S block. Helium is a non-metal in the non-metal zone, but it's written in the P zone, even though it's an S block. So sulfur, thank you, Sam, for being brave. Sulfur is 1s2, 1s2, 2s2, 2p6, 3s2, 3p4. And that is your electron configuration for sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. Boom, bada bing, bada bam. All right, so let's do titanium because we don't have time for your questions. So, yes.
It actually makes sense.
How did you get that?
I read left to right. So let's keep going. It'll make sense. Titanium. Let's do titanium. All right, guys, we're rolling. This is my jam. This is when I fell in love with chem, right here. Okay, literally the quantum mechanical model is when I thought, oh my God, chem's the most amazing. 1s2, 2s2, 2p6, 3s2, 3p6. We're trying to get to titanium. 4s2. Okay, note D block. Once we hit the D block, we're one energy level lower than we think we are. So it is 3d2. So it becomes, yes, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And if you're like, hold up, energy level 4 is a greater energy level than 3. How is the D block relatively higher in energy? Why is it being filled later? It's because there's technically sub energies that are slightly different and greater out of the order of the energy levels that are acquainted with or associated with your suborbitals. But it's because it's due to an effect called nuclear shield or penetration is what we actually call it, because the orbital shapes allow it to have access to the nucleus better than other orbital shapes. Yes.
But just because 3d2 is after 4 is still the same as electrons.
Yes, 4 is still your overall greater energy level. It's just that the relative orbital is slightly higher than the 4s. Olivia, that's the right face you should be making, the question mark face. Absolutely. So we're going to move on because you're going to have plenty of practice. And that's how we write out electron configuration. But notice something. We only address the first 2 quantum numbers. We need to upgrade our system. Okay, so we're going to upgrade it to the orbital diagram. And this is where, for all of you that like arrows, this is your moment to shine, you physics crazy vector people. Yeah. So orbital diagrams allow us to show electron spins as the relative energy status and the relative energy status of an electron in an atom. So this is what it looks like. You can do it vertically, vertically or horizontally. But the idea is now, notice something. You're not only representing the energy level or the principal quantum number in the orbital, now you're also representing the various orientations, the suborbitals, okay? And you're representing the spin up and spin down. Did that glass just splatter? I hope not. Okay, I'll just go over and put my hand down and see if I feel anything.
yeah.
So what we have here for an example is sodium. Sodium's electron configuration, EC, right here, this is EC. Electron configuration is 1s2, 2s2, 2p6, 3s1. You read across. But that's not enough information. I want to know, is my specific electron up or down? And which orientation is it in? Which suborbital is it in? Which degenerate orbital is it in? Okay, so what I could do is either is correct. These are equal. What I do is I label, I create little boxes, or what I like to do is write like this. 1s, 2s, all of this is 2p because 2p has 3 orientations, 3 suborbitals. Each holds a max of 2 electrons. Aufbau principle says I must build from the bottom up. I must fill from the lowest to the highest relative energy level. So what I would say is 1s2, 2s2. Watch how I fill in 2p. 2p6. There's a reason I don't pair them up immediately. I don't pair them up immediately because there's a rule called the Hund's rule. And the Hund's rule tells us that when degenerate orbitals are being filled, the most stable configuration is the one that maximizes, where does my note say? Maximizes the number of unpaired. Okay. Oh, I see how I wrote it actually here. I wrote it all out. Number of unpaired electrons with same spin. We always start with the up spin, right? Because we want to start positive. We want to start positive. We always start with the up spin. So here's how you can think about it. When you're in a home, and I'm assuming you all know what bunk beds are. If you have a bunk bed, okay, and you have 4 rooms with bunk beds in it, you probably, unless you're really close friends with the person and you're just like, okay, to be with them, you probably are going to choose their own room first and hope, Lord willing, that no one comes and also resides in the same bunk bed. You want your own room first. Same with electrons. If they can get a suborbital to themselves, they will. And then they'll partner up if they have to. Okay. So, and then of course we didn't finish it. 3s1. So I personally like to draw lines because I get lazy and I don't want to draw a box around everything. The same information is being conveyed. You could graph it vertically so you can show the relative energy climb, because that's essentially what it's showing is the relative energy climb. Okay, so what we see is lithium. Its electron configuration is 1s2, 2s1. What you see is 1s, 2 arrows, opposite spin, and 2s. And then you increase. What do we do when we build from the ground up? Beryllium adds 1 electron. We just add 1 more arrow into the soonest available, lowest energy spot to be occupied. Then we do B, boron, okay, right after beryllium in the 2p1, okay, it ends in the 2p1, okay, and we add an up arrow into one of those suborbitals, one of those orientations, one of those magnetic spin numbers. Yeah, it's a lot of terminology for the same thing.
So your lines in those boxes are the same.
Equivalent. Equiv. All right. Hello. Goodbye. I'll talk to you another time. Okay. So try drawing an orbital diagram horizontally for nitrogen. Start with figuring out the electron configuration, then draw its orbital diagram. Same thing with carbon. Okay. Here are the answers. For those of you listening on the recording, these are the answers. Notice Hund's rule. You stay single as long as you can until you have to pair up. Okay, I recommend that for a lot of things in life. One of my students just said projection, potentially, but I've learned a lot in life. I think it's really good for you guys. Anyway, moving on. So how do we start looking at, don't worry, Maggie, you'll probably break up. How do we look at, sorry, but it's true. So, how do we understand valence electrons, okay? I keep on mentioning these. They're super important. They're radically important, actually. All right. And it's the electrons in the outermost energy level. Now, it's the outermost filled energy level, like one that has electrons in it. Okay. Because technically the outermost energy level for everybody is 7. but not all atoms are going to fill the 7 rings or the 7 orbits or updated version 7 principal quantum numbers, right? 7 energy levels. So it's the electrons that are in the highest energy level. So the Bohr model, it's the outermost ring, right? The outermost ring or orbit. Okay. In the electron configuration, it's the electrons in the highest energy level. So here I have 7 valence electrons. VE is short for valence electrons. These, by the way, are the most important electrons because what they do are they're the ones that do the bonding. They're the reason. It's kind of like saying your outermost valence electrons are like your appendages, and your inner core electrons, everything below it, are your like intestines. You interact with the world through your arms and your legs. You do not interact with the world through your small intestine going out to handshake somebody. Okay? That's very Stranger Thing-esque. We don't do Stranger Things in here, okay? The upside down is not for us. All right? Though there will be moments where you feel like you're in the upside down, okay? So, when we look at our previous examples, our valence electrons are these 4, these 5, titanium, this 2. Hold up. That's not the last one in my electron configuration. You're right, but it is the highest energy level. So I would still only have 2 valence electrons for titanium, but the electron configuration would tell me that the suborbital of 3D is technically a wee bit higher than the electrons in the suborbital of 4s. And this one. And these 6. Those are my valence electrons. They're the ones that make the magic happen in chemistry. Those, remember, the superscripts are the number of electrons.
And sulfur, wouldn't the last one be the valence electron?
It's highest energy level.
Oh, so it
Principal
doesn't
quantum
matter
number.
which one?
Doesn't matter the orbital.
Okay.
It's this subscript is the number of electrons.
Superscript. Gee willikers. I'll fix that. Man, I had like 4 people look over this. How did none of us catch that? Okay, superscript. Could Charlie, could you go in and fix that for me? Page 11. Superscript. Ah, wow. Wowza. Okay. So, let's move on. We got 2 more pages of notes to magically do in less than 30 minutes. Let's do this. So, how many valence electrons for beryllium, sulfur, titanium? We just answered those questions. I'm going to say refer above highlighted yellow. All right, so let's take a look at these special cases. I've mentioned ions before, charged atoms. Do we ever mess with the proton number? No, right? It's kind of like messing with your DNA, genetically modified. That's a little weird with when it comes to people. Although, did you guys hear about like what? It was like a German lab or something? That is it Chinese? Man. Anyway, okay. Well, you know what? Okay, so they just recently are saying that like in the coming years, they have made their first baby simulation of a woman's womb to like genetically grow like preferred little children in like a simulation vat. And I was like, but how did I get off on that? DNA. So we don't mess with the protons. All right, guys, we don't mess with the protons. I know I teach very ADHD, but internally I'm actually quite linear, but like, you know, ions, okay, cations. Don't forget, this is when you've lost electrons. You have an overall more positive. Anions, this is when you've gained electrons. You have an overall more negative. So what we do when we talk about electron configuration is, let's say I have beryllium 2+. I don't just have beryllium, I have beryllium 2+. My 1s2, my 2s2 configuration, I would take from the valence shell. I would take from the valence energy level. So I would take both of those. And my new configuration would be 1s2. Okay, so we take from, okay, valence energy level, outermost energy level. Okay, now what about anions? Let's say I am fluorine. because we're flooring it, okay? Get it? Jokes? No? Okay. All right. Okay, so I'm flooring 1 minus. By the way, for charges, we always write the number, then the sign. Number, then the sign. It will matter. If you write it opposite, you're telling me something totally different. Okay, I have 1s2, 2s2, 2p, 5. Okay. So what happens is I originally have 7 valence electrons. I add an electron to my valence shell. So what I do is I say, hold up. I am going to now add 2 valence. And I'm going to add to this number. So +1 equaling 2p6. So now what I have is 1s2, 2s2, 2p6 is my actual ion configuration. Makes sense. Alec first.
Add electrons past all the defined shell, as in.
No, not according to ground state configuration, alpha principle. Next.
I was gonna say, could you have fluorine 2 minus?
You know.
No. Okay.
No, that would never happen. That's just not physically possible in the world. Yeah. Great question though. So, here's kind of an example of what it would look like on the Bohr model. Okay, what you see is you got rid of this one, x to the nay, nay. Okay, and then you have chlorine. You added one, so now you have a complete octet. Ooh, that's a special word. When you have on the Bohr model 8 electrons in rows or orbits 2 through 7, that is a great place to be. That is stability to the max. Okay. When you have a full S&P orbital, max 2, max 6, you have a total of 8. That's the electron configuration way of understanding octet. Stability to the max. Notice who has a full S&P. The noble gases do. That last column do. They're the end. They're the goal. They're the royals. Okay. We noble gas. Sorry, not St. Marcos. Whoa, sorry. I did teach at St. Marcos for 1 year, so I apologize. But we say that electron configuration for ions create an isoelectronic configuration with another element. So sodium is now isoelectronic, has the same electron configuration as neon. But what's different about it? It has a different proton count. That means it's still sodium. It's just charged sodium that electronically looks like neon, but it's still sodium because it still has its ID number, its proton count. Okay, chlorine is isoelectronic. Chlorine anion is isoelectronic with argon. Okay, and good. How is your brains doing? We're doing great? Great. So we're moving on. So when ions form, electrons are added or subtracted to the valence energy level. Valence. So that means if you have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, you would not add or subtract from here. You would add here. Oh, you would only subtract from here. Just kidding. You subtract from here, but then you would add here. Here you would subtract from here. And here you would add. Transition metals, once you start getting transition metals involved, they're really funky dunky. Really funky dunky.
So you don't add electrons to the valence level?
You do, as long as you don't hit the energy level difference with the D and F orbital. As soon as you hit D and F orbital difference, now it kind of changes the name of the game. But standardly, for all elements 3 and above, standard thing, add normal 4s. But notice the progression shifts, right? So, yeah. You rarely will be asked to do at that level of, you're rarely going to be asked to work with inner transition metals and transition metals, at least from the electron configuration standpoint. All right. Okay. I already went through fluorine. Okay. I already went through fluorine, so I'm going to say look above. Why don't you try manganese normal, neutral manganese versus manganese 2+. Go ahead and give that a shot. So this is what you should have gotten for the original electron configuration of manganese, Mn manganese. Now I am losing 2 electrons to get an overall positive. Okay, so what's my valence shell? I'm going to take from here. So now my electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Feels good, folks. Feels good. So, yes. Because it's about penetration and nuclear shield effect, which it's okay. So yes, I know it's a bad word, but it's what we say. So the d orbital is a clover leaf. Okay, the clover leaves have a little dying tip at the end. Okay, the p orbital and the s orbital are very round. They're very volume-esque, right? Okay. The d orbitals literally puncture into the area in between, and they get closer to the nucleus. So your electrons in that probability wave area are statistically in a position that is better oriented to be attracted to the nucleus, which is why, relatively speaking, your 3D, okay? Oh, 3D is actually higher. Oh, it's because the shielding. Okay, got it. Sorry. So, sorry. So it's higher because the p orbital and the s orbital are blocking the 3D. That's right. Despite their penetration, they can't really quite get there. So it's coefficient. Yeah, big number. Because the big number, okay, sorry guys. Ooh, I shouldn't have recorded that. Ooh, if I could rewind, I would, but I'm too lazy to cut that. So start over. So nuclear shield effect. This is why 3D is at a higher energy level than 4S, because the 4S is circular. It literally chunkiness blocks the 3D. We don't say that nowadays. We say there's more of you to love. Okay. So there's just more of the 4S to love that's in the way of the 3D getting the love that it needs. Okay, guys? Because it's an S. It's an S is volumetric. An S is like me after Thanksgiving. Okay? That's what an S is. All right.
Just have to remember that the valence electrons are always the ones with the highest energy level, the highest
Yes.
coefficient. You're only dealing with the ones with the highest.
Yes. Highest number, highest big number, highest energy level, valence electrons. Okay. So what about excitation? Because electrons get excited. Remember, this all started with the excitation of electrons, the excitation, the release of a photon, the release of a wave with a discrete amount, creating a unique emission spectrum. How does this all connect? Okay, so excited wise, what we see is an electron, okay, will jump to another energy level. Okay, so it'll jump up to the next, oh, I think I meant to put it here, jump up to the next energy level. Your excited electron configuration is just you pushing up the electrons. Okay, so that's all I'm gonna say. Now, electron configurations can get really long. Like, try writing the electron configuration for like antimony. Antimony is SB, by the way. Antimony is SB. Antimony has the symbol SB. I don't know why. It has to do with it's either Greek or German, or sorry, not Greek, German or Latin name. I wasn't around then. Okay, I'm older than you, but not that old. Okay, the gray hairs may say otherwise, but I got those in junior high. So, okay, so let's take antimony for a second. Antimony is a nasty beast. Okay, step one, identify the noble gas. Okay, or column 18, element before your specific element. Before your element, whatever your element you're talking about. Okay, before your element. You will soon become masters of interpreting my Apple Pencil writing. Step 2. Okay, box. Put into brackets that noble gas that you identified in step 1. So for antimony, the noble gas before antimony is krypton. Superman. Well, it's not kryptonite, man. It's krypton. Right? Hold on. It's Krypton. Well, I doubted myself. I was like, Krypton. What that does is that bracket right there tells you all of the electron configuration that would be required to write up to Krypton. Bam, done. Done. You don't got to write it. It's there. Now what you do is you pick up where you left off. So then you pick up where noble gas left off. So until you get to the element of your desiring, of your choosing, of your hopes and your dreams. So it would be 5. My eyesight does not handle this well. 5s2. Okay. 4d, no worries. 10. 5p3. Thank you. And that right there collectively would be, okay, Krypton, 5s2, 4d10. You're welcome. 5p3. This is the noble gas electron configuration for antimony, 4sb. And then of course that means your iso, oh, nope, and that's kind of it. We've already actually talked about isoelectronic. I don't really feel the need to go over it again. So I'm going to send, again, refer above because I'm just that good. Refer above because Miss Judy. And by the way, I like my name Miss spelled M-I-S-S. I don't know why, but it just feels better to me. So if you write me a note, M-I-S-S. Miss Judy is a whiz. Smiley face. Okay. So how do we electronically prove that this is real? Where are the instrumentations? Where do we do this in lab? It's called a photoelectron spectroscopy spectrum. This is a very common MCQ. So what we do is when PES, okay, PES, what we say is that we bombard a sample of an atom, typically unknown, right? Because the idea is that you're discovering something about it with a bunch of energy, electron. We just like shoot it with a laser. And what the PES, photoelectron spectroscopy, does is it tracks the energy required. Did I spell that right? Yeah. Required. I think I did it the French way. To remove each electron from an atom by shooting photons. Now we know our photons are particles of energy with discrete amounts of energy. So that means we can literally quantize the amount of energy that it required to break it off by counting the amount of photon energy we needed, which then in turn tells us from a backwards perspective, the amount of energy that was holding on to that electron in the first place. Okay, it tells us an idea of how close it was to the nucleus, because the closer you are to the nucleus, the closest you are to your Bohr thing, the more stable you are, the less likely you're going to be pulled apart. Okay, until college comes. So, sorry, y-axis is your relative, okay, amount of electrons, okay, and your x-axis is your binding energy. Now, something to note, or the energy required to shoot off an electron, the energy to break what was binding it together, okay? Now, something you should notice is that the megajoules per mole is a new unit. We don't use mega very often. It's a lot of energy to remove an electron. It's called the strong nuclear force. It's one of the 4 main forces in the world, okay? In the universe, actually, not just the world, the universe, okay? The strong nuclear force is a beast to overcome. So you're gonna need a lot of energy. Also, something to note is that higher energy means closer to nucleus, which means you're gonna be in lower energy levels. From the PES, the photoelectron spectroscopy spectrum, you can literally graph out the electron configuration. So what we see here is that a small peak, such as this one, okay, would be, the first peak is always going to be your 1s peak. Like literally it's going to be, the smallest peaks are always going to be your s orbitals because they can only hold 2 electrons. Y-axis ratio, there's maxing out at 2 electrons. So your small s orbitals will always be the shortest peaks at any point. And the first peak will usually be your s orbital because why? It's the closest to the nucleus. Okay. If you're 3 times larger, right? You're the p orbital because p orbital can hold 6 electrons. Now, if you're a partially filled p orbital, you might be a ratio. If you're 4 out of the 6, you're going to be twice as large as the s peak because the s peak is 2. You filled it. You moved on to p. Now you have 4 out of 6. You're going to be twice as large, but it could technically have the capacity of being 3 times as large. Okay, you're 5 times larger than the S peak is going to be your D, and then your 7 times larger is going to be the F. So what happens here is what we see is according to peak. Let's look at this example. Okay, this is a little unique because what we see is they actually they reverse the x-axis. We actually tend to see that they write this number over here. This actually usually is a huge number. They actually normally graph this with the highest amount of energy first, and then you go towards 0 to show that you're getting further and further away from the nucleus. You're getting into higher and higher energy levels where there's less attraction being held on. So it's easier to rip it away. Kind of like ripping candy away from a baby, right? The weaker it is, the farther away it is from mama bear, the easier it is to snatch it, right? So the candy, not the baby. So what you see here though is if the idea is this, 2s, this is a ratio of 2. Sometimes each line represents a ratio, a 2. Sometimes each line is 2. Instead of being each line 1, you have to look at the ratios. You have to look at the relative size of the peaks, okay? And then what we see here is, since each line represents 1, the next peak, 2p, because you had to fill the s to get to the p. Like, this is not excited state electron configuration, okay? Is 1, 2, 3, 4, 5. And that's how you would know it was a 2p5. Now, if you're asking yourself, how did I know it was a 2? I'm telling you right now, this is a little snippet. This is a 2. This is the 2 zone. You will most likely be given the whole thing, okay? So that's how we do it. It's your easy wins on an AP exam and my exams. And that is the end of lecture for today.